finish off chapter 10, everyone, and we're going to basically just do some more SALT questions. They have a theme to them, so I would hope that we've done plenty, but a few more won't hurt. And once we've done that, we'll be finished as far as the homework, what you need for homework for this week. And I'll just start the next section, get a head start. And the next section is going to be how you estimate the value of the difference in two proportions. And we've kind of met that, and we'll do a number version of it, and then we'll show you how you can do it in SALT. So let me jump over to the homework, and I've got that double window thing set up that seemed to work pretty well yesterday. So we'll try using it again today. So in a national, this is question 16. I'm going to do two of these questions, I think. In a national survey carried out in 2009, 58% of the randomly selected sample of American adults. Oh no, we did that one. Didn't we do it, the abortion one? Yeah, let's not do that one again then. Okay, let's do 17. In 2007, they had a survey and it was interested in, do you think penalties for underage drinking should be made more strict or remain the same? And the sample responded that 61% of them said that they should be more strict. This result will be used to estimate the proportion of adults in the United States who think that the underage drinking should be more strict. So it's a basic sample of 500, 61% said, yes, it should be more strict. Now they begin by one of those, what's the population? In this story, would you agree that, if I can find it again, and it's here, you see all adults in the United States. So I had to read a little bit. So go through one of them and it's a proportion. The population parameter is all the adults in the United States. And then it goes on and it says calculate the standard deviation and the classic 95%. And then, you know, that classic sentence that they finish with. So I'm only going to use the SALT to do this. So write down the numbers because they're going to disappear. Oh, I just noticed something. Didn't they tell us 61% of 500? Right. Watch what happens when we kick over into SALT here. Click on one sample proportion, and there's our problem. It doesn't want to know that it's 61%, right? Don't we have to find out how much out of 500? Not 61% of 500, but exactly how many that is. So I grab my calculator and I find 0.61 times 500. And I find out that that's the same thing as 305 out of 500. Are we good with that? Right. Now, where do we go next? We hit confidence interval. And yep, 95, so it's in the right place, generate results. And can you see that the lower limit is this number, about 56, 57%. And the upper limit is about 65, which is that guy. And the standard error is here. And all I'm going to do now is round it off to whatever accuracy they're talking about. So they want 6 decimal places, which means all of that one, but they only want 3 for this one. So that's who you get. And you want 3 for this one, so that one rounds up to a 3. So somewhere around about 56 to 65% of Americans probably think they should be stricter, right? Which I would say then is what? The majority of Americans, anything more than 50% is a majority. So if that was how you were going to decide, you would probably say that more Americans, adults than not, think it should be stricter. And that's pretty much the end of that one. So the second and final one I want to do is this little story here. In a nationwide poll done in 2009, the proportion of respondents who thought it should be illegal to use a handheld phone, driver, whatever you cell phone, I don't call it what it is, a cell phone while driving is 82%. And the sample poll was 900. So I'm writing that down, 82%, and it was 900 people. So I'm going to my calculator and finding out how many people that is. And it's 738. So when I go over here, oops, click on it. When I go over here, it's 738 people out of 900 think that it's illegal or should be illegal if it's not already. And they wanted a 95% confidence interval. So that's the one that's been set up right now. That goes here. And the upper limit of the 95 is here. And they want it to 3 decimal places. So that turns into a 5. And that stays. And if I scroll over here, we have the standard error. Let's see what they want. Okay, standard error. Based on this sample, we can predict that somewhere between almost 80 to 85 is what we think the real answer is if you asked everybody in America. Right, so we've got a pretty good ballpark figure for where it is, and that's based on a 95% confidence interval. Now, if you want to do a 98, which is very unstandard, but they want it, so we'll do it. Don't you just change this guy here to 98 and regenerate. And when you do that, the confidence interval will change a little bit. Since you want to be 98% sure that you've got the right answer in your interval, won't this one be a little bit smaller? Or sorry, a little bit larger, I should say. So instead is, wait a minute, 98? Something's not right. Did I generate results? Something is not right. Is it my eyesight? 95. Generate results. Okay, that's correct. You want 98. Generate results. The reason I'm hesitating here is that I can't see any, well, not much change. 845 is now 849. I guess it is a change. But the 7901 is a little bit weird. Let's put it in. There is a change there. Would you agree it's a little bit bigger? What was worrying me is that it's almost negligible how big it was, wasn't it? Only like the third decimal place wiggled a little bit. I was hoping to see like a 0.82 and, you know, some noticeable, but it is bigger. Would you agree it's a little bit bigger, but not that much noticeable, which is kind of why I was hesitating. So which interval is wider? Bigger is wider. Would you agree that 98 is wider? If I did a 99, wouldn't that be even wider still? Right? And if I did something crazy like 99.99, right, which is pretty much guaranteed that I'm going to get it in the interval somewhere, right? 99.99%. Do you see how big the intervals are now? 70, 70, 86. So you could be pretty sure if I did that kind of confidence interval, that somewhere in the range 77 to 87 is the correct answer for the population of all America that believe that that's the case. Are we good? So if I gave you a proportion story similar to these ones, do you feel comfortable about using salt to get the interval and maybe answering some questions after that? Oh, good. So let's move on to our next section then. And it's really not that different, right? It's the same kind of thing. It just takes it to the next level. So it's still part of chapter 10. The difference is that we're now going to estimate the value of a difference in two proportions. And I'm going to do the first one totally by hand. And then we'll zoom over to do salt and have it. So I'm going to do a classic double-blind experiment. A pharmaceutical company have developed a new drug in my story. And this new drug improves asthma, right? So in other words, if you've got asthma and you take it, you have less asthma attacks, right? It improves your life in some way, right? And they're a way of measuring that, you know, like what percentage of the week do you have asthma issues, right? Whatever way they do it. So they measure it in some way. And they have an old drug and they have a new drug. And in the old drug, they randomly have a sample of 1,000 people. We'll call them N1. And the new drug, they have 2,000 in that sample. And the old drug, the percentage of people who had benefit, right, improved their lung function, whatever you want to call it, was 750, which, by the way, is 75%. So it's a pretty effective drug, right? If you take that drug, you know, your symptoms improved, right? You have less asthma attacks, 75% of people. And the new drug, the pharmaceutical company, think that their drug is better than the old one. And so the 2,000 that they had, let me pick a number. They had 1,560, which ends up being 78% effective. And we want to see whether or not that is enough evidence to prove to the FDA that that new drug is effective. We'll assume that it's already jumped over all the other hurdles. If you look into how do new drugs get on the market in America, there's quite a lengthy process. It's very expensive for the pharmaceutical companies as well. The first thing they have to do before they even prove anything else is that it's safe. So they get volunteers and they get the drug and they look for side effects. And if those side effects are, well, some people are nauseous or some people, you know, their blood pressure goes up a little, then that's probably not going to cancel it. But if some people are violently sick, or God forbid, some people died, that drug's gone, right? It leaves the market. You're never going to see it. And they tend to do that, at least in most situations, as the first line of defense. So a dangerous drug doesn't even go on the market. So we'll assume that it's past that level. Then it goes into full trials, which is what this is. So full trials would be a large proportion, 2,000 in this case, of volunteers. In fact, the world would start off with 3,000. And then some of the patients would get the old drug and some would get the new. But the way you would make it double blind is you'd make the pill, let's say it's a pill that you get, the same pill. It looks the same, everything's the same. The only difference is the old drug has the old drug ingredients in it and the new drug has got the new drug. So you see, the patient doesn't know if he's getting the new drug or the old drug, right? And the doctor who, you know, checks him every month, whatever, as part of this process, neither does the doctor know which of the two drugs he's got. That's what makes this story double blind. They try as much as possible when they do a clinical trial to do double blind. It's considered the most accurate way of telling if something's doing a good job or not. Would you agree? That probably makes sense. You don't want people to know, oh, I'm getting the new drug. New drugs are obviously better than old drugs. It's going to make me feel better. My asthma is maybe not quite as bad because of that. And it's all done by the way your brain can make you feel better if you believe something strongly enough, right? The placebo effect, as it's called. Well, we're ready to do an analysis on this. And the way we're going to do the analysis on this is that we're going to get a 99% confidence interval. And to do that, we need to collect some information. And it's going to be a 99% confidence interval on the difference between them. Now, before I do that calculation, let's look at the three things that might happen before they do happen. Now, the difference we're talking about is going to be P1, take away P2, right? Old drug, take away new drug. That's going to be the order. I could do it, and I find out that the range for the difference is negative 0.11 to negative 0.02. Right, if you notice that all these numbers are negative, we've talked about this before. All these numbers are negative. What does that tell you about the connection between P1 and P2? Is P1 a bigger percentage than P2, or is it a smaller percentage than P2? What would this interval be evidence for?
That it's smaller.
Right, and I'll use this less than symbol, right? Agreed? Seen that before. It could be that you might get 0.02 to 0.06. I mean, I guess that could harm, right? Now, in that case, wouldn't it, because everything is positive, wouldn't that be evidence that the old drug is actually better than the new drug, which would be bad news for this pharmaceutical company, wouldn't it? And of course, there is one third possibility. Couldn't you get the interval containing 0? Can you remember what we do when an interval contains 0? What's the kind of sentence? You don't need to get exact words, but what's the gist of the sentence that we write down when this happens?
Too close to call.
Too close to call would be in the voting world. I would agree with that. I might choose a different phrase, but too close to call works. Right. There's no evidence of a difference. It may not be exactly the same words I used last time, but that's the gist of it, isn't it? There's no evidence to prove that there's a difference. Right? There might be, but there's no evidence to prove it. Right? That's all that says. Nobody wants that one. Isn't this clear cut? You got some evidence, something. This one is you just spent a lot of money, but nobody can tell. Well, let's move on to the calculation stage. P1 hat take away P2 hat is going to be how we estimate the difference. And in this case, it's 0.75 take away 0.78, which is negative 0.03. Isn't that good news for the pharmaceutical company? Right? You can see it here. Isn't it about 3% more effective? But couldn't that just be with the randomness that you get with samples? Right? If you did it again, you might get slightly different answers, and sometimes the different answers are big enough that these two could even switch places. Couldn't this be the 78 and that be the 75? Right, that could happen too. And so we have to go through this much more formal process. Now we have to calculate a really ugly guy, but you've met this guy before. So this is kind of same old, same old. Any volunteers for the formula?
P1 minus 1 minus P1 over N1.
Agreed? And? What else?
P2.
Yeah. And all the
P1
other
minus
stuff that goes
P1,
with it.
or
Yeah.
P2, excuse me, over N2.
And so in this case, we are going to be using these guys. 0.75. Take that away from 1 to get 0.25, and then divide it by 1,000. Then you're going to add 0.78, take that away from 1 to get 0.22, and you're going to divide that by 2,000. And we go to the calculator, we go square root of 0.75 times 0.25 divided by 1,000, added to 0.78 times 0.22 divided by 2,000. And the answer I get, I'm going to have to round this off somehow, so 0.0165. Okay, so 4 decimal places. Now, we're going for a 99% confidence interval. Now, I'm going to use the empirical rule, which is less accurate than the way SALT does it, but it's an easy to remember formula. It's the difference plus or minus 3 standard errors. Now, if you want to know what the more accurate version is, it's 2.58. And if you want to know the ultimate accurate version, now, it's not that these are different. Would you agree? They're going to give different answers. It's just that this one is the easy one to do as a calculation, right? 3 standard deviations. And these two are essentially the same, but in some textbooks they use 2.58, and other textbooks they use 2.585. Isn't this a good argument for why we should always standardize our answers? In other words, shouldn't they have a conference somewhere where people say, let's not use this, it's too inaccurate, let's use this one or that one, and whatever one you decide to use, that we all use it. And since I've got 3 versions of the same guy, which one of those 3 do you want me to use, just to show you it being used? Because there's not a lot of difference in the calculation, just the number that you're going to use. So which one would you want me to try?
Just the 3, it's easiest to remember.
Let's do that one. So 0.0165, and I've just put the wrong darn number down, negative 0.03 is the difference, plus or minus 3, 0.0165. So it's negative 0.03 plus or minus, let's do that guy times 3, 0.0165 times 3 is 0.0, let's just call it 0.5. Would you agree it rounds off to 0.5? Right. So if you take this guy away, you get negative 0.08. And if you add this guy, you get positive 0.0, all bad news. Isn't this the situation where there's no evidence that there's a difference? Now, there's no evidence that it's worse either. Would you agree? But there's no evidence that it's better, right? Because it could be a little bit worse. It could be a little bit better. You can't really tell here. And that's on a 99% confidence interval. I'm going to do this question in SALT in a few moments, and I'm going to play about with this percentage to see if we can make this interval different, which we can, but whether we can make it in a way that's going to help. Oh, before I forget, what do we call this piece of the answer? It's got a very special name.
Margin of error.
And isn't it probably going to be as a percentage? So wouldn't this answer be -3% plus or minus a margin of error of 5%? Most people like percentages, don't you, than decimals. But just in case you get questions where you do it in percentages. So, are we cool with this process? How to find a confidence interval, in this case 99%, for the difference in two samples. So what we're now going to do is nip over and do it on SALT. And there's going to be a little bit of differences in answers. And that's because SALT does the most accurate version it can. So see that 2.585 thing is probably one of those guys, or maybe even more decimal places than 2.585, right? So give it a little wiggle room when we do it. Okay, so over here, I'm going to go, actually, let's just kill this off because I only need to see that, make it a little bit bigger even. So instead of one sample proportion, do you see we now move to two sample proportion? Do you see the name's different? Right? Two sample proportion. Click. Number of successes. Well, I've got my data in front of me. So the old drug had 750 successes out of 1,000 people who took part. And the new drug, which is number 2, had 1,560 successes out of the 2,000 who did that. And we want a 99% confidence interval. And we got -8% to -8 to +2. And what did they get? And do you see how their limit is about -7 and a bit and +1 and a bit? Do you see the difference? Now, if you'd use 2.58, can you trust me, your numbers would be very, very close to that, right? Now, are we good so far? I'm going to kind of, yeah, I think I will write that down because I'm going to change the numbers and it might be hard for us to see. And I'm also going to round them off. So this is a 99% confidence interval. And it was -0.07 to +0.01 to 2 decimal places. Right. I'm about to make this 95% confidence interval. Is that interval going to get wider or narrower? If I'm going to be 90, agree, it's going to get narrower. Let's see how much. It's going to go now at the 95% confidence interval. It's now narrowed down to essentially -6% and 0.00, like 002, but right, 0.00. And one last one then. I'll now knock it down to 90%. Shouldn't that even be narrower? And when I click on that one, I'm going to get at 90% that the confidence interval is somewhere between -5.7, that's basically -6%, and -0.002. I'm going to put the third decimal place in so you can see it. Let's see the effect that changing what confidence interval you choose to represent this information has on your conclusion. When you used a 90% confidence interval, aren't all the numbers negative? So if you're 90%, if you only want to be 90% sure you got it right, isn't the old drug not as good as the new one, right? It's less than. Isn't this one, yeah, well, I don't want to write no evidence again. How about no evidence? Would you agree that this one is almost okay, but still no evidence, because that is still slightly positive. But when you got to this one, it became evident. Now, if you are trying to make money, wouldn't you go for a 90% confidence interval when you try to prove that your new drug did better, right? Now, the good news is that you're not allowed to pick your confidence interval, because if you did allow them to do that, wouldn't they cherry pick the right one? So the FDA has a fixed confidence interval level. I don't know what it is. I'm sure if I went in, I could find it. But let's say they say 99%, right? So it has to pass the 99% threshold before it's considered. And the FDA are pretty strict about new drugs on the market. One of the rules that they have that they try to stick to is that you can't introduce a new drug unless you've proven that it's more effective than the old one. Proving that it's just as good as the old one ain't going to cut it, right? Why should we have another, blood pressure medication if it's not going to improve the success rate, right? Might as well just keep the old one, because at least we know the long-term effects of the old one, right? Because it's an old one, right? It's been used for years. What happens when a new drug is effective? Let's suppose the new drug was, 6% better than the old drug. Let's suppose we could prove that. Well, what happens when you go to the doctor and you need to get your asthma medication? Do you get the generic, which is the old drug? But what happens if you want the better drug, the new drug? What's the price like? Any of you ever had a new drug because it's actually the only drug out? I've had a drug. I got, it's now thankfully went generic. And one of the drugs I get for my illnesses, when I first got it, it costs $700 a month. Yeah. And thankfully I had insurance, so I only had to pay 20% of that, but that was $150 a month on it. And now it's gone generic. I still have to pay $70 a month on it, but at least it's half what it used to be. There are a lot more drugs. Have you ever read stories about people having drugs that cost $5,000 a kick? That's, an issue that other people are working on. There are arguments, which I'm not saying I totally believe, why the pharmaceutical companies charge so much for a new drug. And one of the arguments that they give is that for every successful drug that they bring on the market, they've spent millions on failed ones that never worked. And so for them to stay in business, the successes have to not just pay for the cost of the successful one, but the cost of the other 4 failed ones before they found the successful one. So it's quite an expensive thing. And so to get their money back, they initially charge a lot. That's the argument, at least, that they give. I think, tell me if I'm right, is it 5 or 10 years they get where they can do what they like, but after that it goes generic? Does anybody know any in the nursing field?
I want to say it's 5 years, but depends on the drug, because sometimes they're longer because they take longer to develop.
Okay.
There's
So-
also the fact that they can change one aspect of the formula and reset the copyright on it. They did that with inhalers. They changed the propellant and was able to extend so they couldn't be a generic inhaler.
But what stopped me from using the old version? The old
Did it?
propellant?
They didn't manufacture it anymore.
Oh, the sneaky buggers. Yeah. Okay, we cool with that, right? Would you agree that what we've got here is pretty much the same idea, just a little bit more details? So I've got time for one more, but this one's going to be done purely with salt, right? So let's collect some data on something. Made up story. I wonder if there's a difference between Pepsi and Coke, because it's Friday and I have no imagination. So we went out there and we collected 400 people. And, oh no, I'm going to have two groups, aren't I? Oh yeah, we gave a blind taste, right? And 400 males and 600 females. And we asked them, we gave them both drinks, so they didn't know which one was which. And we asked them which one did they prefer. And for the males, 300 out of the 400 liked the Pepsi. And for the females, it was 280 out of 600 liked the Pepsi. So what I'm testing here is there a difference between males and females and liking Pepsi? Do they like Pepsi about the same amount, or is there a difference, right? So that's what I'm going for evidence on. So 75% of the males said they liked Pepsi as opposed to Coke. 280, 600, and it's about 0.467 on the females. Right, that's all the numbers I need. Let's go and see what we get. Do you think this one's going to be significant? 75 compared to 46, you think that's a big enough difference that the evidence should shine through? I think so. What do you want? A 99%? I should have put that in the story, shouldn't I? 99% confidence interval on the difference. So the males, 300 out of 400. And for the females, 280 out of 600. And I said 99. Isn't that the highest hurdle to cross, right? 99. And let's see what we got. Ooh, we have got that's not right. There we go. I didn't hit generate. That's right. I was wondering there for a minute. So the lower limit is roughly 0.206. Let's call that 21. And the upper limit is 359. Let's call that 36. So let's return back to the whiteboard and see what we've got. A 99% confidence interval says that the difference between them is 21 to 36. In other words, males like Pepsi 21 to 36% more than females like it, right? A quite noticeable difference, would you agree? Quite a clear separation. And that is based on a very high confidence level. So if this was real data, wouldn't you be really comfortable about writing an article and saying, yeah, it's guaranteed men are different than women when it comes to taste in Pepsi? Why that would be even very interesting to read about, who knows, but it's true, if this data was true. anything to finish with? Because we're pretty much done for today.